Hello everyone, I hope you are doing well. In this video, we are gonna solve problem 6.6 from chapter 6 of Fundamentals of Statistical and Thermal Physics by Reif. Alright, this was the book name. Okay, Fundamentals of Statistical and Thermal Physics was the book name. Let's see the problem statement and we'll dive directly into the solution. And the statement says a system consists of capital N weakly interacting particles, each of which can be in either of the two states with respective energies E1 and E2, where E1 is less than E2. Okay, till this point we saw that we have a system of capital N particles and they have two possible energy states, E1 and E2. Okay, that's the crux of what we have seen so far. And since E1 has lesser energy than E2, we can say that E1 is the ground state energy. Okay, that's the ground state and this is the excited state. That interpretation will help us to answer the part A of the question. Okay, that E1 is the ground state and E2 is the excited state, you can say. And in part A, there are three parts actually, we can see here. And in part A, they are saying without explicit calculation, make a qualitative plot of the mean energy of the system as a function of its temperature. So without doing the main calculation, we have to draw the graph or plot for the mean energy of the system against the temperature. Okay, so what is the E bar mean energy in the limit of very low and very high temperatures? Roughly near what temperature does E change from its low to its high temperature limiting values? Alright, so in part A we have to make some good guesses because we do not need to do the actual calculation as they are saying, and we need to make a qualitative plot that doesn't need to be perfect, that doesn't need to be accurate, but it should be really close to what accurate is. Alright, so we'll see how we can draw it. So what we need to do in part A is to draw a graph, and besides that we need to tell them that what is the average energy in the limit of very low temperature and at the limit of very high temperature. At both of these extreme hours we need to tell them what would be the average energy, and we also need to tell them that at which average value of temperature does E changes from its low temperature limit to a high temperature limit roughly. Doesn't need to be perfect. So let's do the part A, then we'll discuss the part B and C later on in this video. Okay, so let's do the part A. Here we can see that E1 is the lower energy state or ground state you can say, and E2 is the higher energy state. Hence, at the limit of very low temperature, all the particles will occupy the ground state energy since they doesn't have enough thermal energy to occupy the higher states. Okay, that is why all of the particles will occupy the lowest possible energy state that is available to them, and in that case we have E1 as the energy state which is the lowest. That is why at the limit of very low temperature, at the limit of very low thermal energy of the particles, all of the particles will occupy the ground state energy, and hence we can say that at low temperature limit, average energy of the particles, we can write it like that: limit temperature approaches to 0, E bar would be equals to E1 simply. Alright, because they do not have enough thermal energy to occupy higher state, which is E2. Alright, this is the average energy per particle, and since we have capital N number of particles, so the average energy of that and the whole system would be equals to E1 times capital N. Alright, this is the average energy of this system at a limit of very low temperature. And probability of particles to be in E1 state becomes almost equal to 1, while probability in E2 state P2 of particles to be in E2 states is nearly 0. Now, as the temperature increases, particles begin to move towards the higher states such that the probability P2 begins to increase and P1 begins to decrease, and P2 keeps on increasing and P1 keeps on decreasing until a point is reached, which is called as a higher temperature limit, a very high temperature at which P1 becomes equals to P2. Okay, the probability of particles to be in E1 state is equals to the probability of particles to be in E2 state. As the temperature increases, particles begins to move to higher state E2. Hence, P1 decreases and P2 increases until a balance is achieved, where both the probabilities become equal to each other. And both states are equally probable. Both states are equally probable. And we can find out their probabilities. For example, we know that the sum of the probabilities should always be equal to 1, and since there are only two states, so there are two probabilities, P1 plus P2 equals 1. And if probabilities are to be equal, it means P1 is equals to P2. We can put P1 in place of P2. It's 2P1 equals 1, P1 equals 1 by 2, which is equals to P2 as well. So the probabilities we have is half, and the average energy of the system at a limit of very high temperature is average energy. We can write limit T approaches infinity, E bar, which is the average energy, equals P1 E1 plus P2 E2. Since we are talking about the whole system, we'll multiply it with capital N, which is the total number of particles we have, and capital N here, P1 is 1 by 2 E1, P2 is 1 by 2 E2. So we can take N by 2 common, 1 by 2 is taken common, so E1 plus E2 is left inside. We can write 2 in the denominator of this thing divided by 2. This is the average energy at the limit of very high temperature, and the transition from lower limiting average energy value to higher limiting average energy value occurs roughly when occurs roughly when E2 minus E1 is nearly equals to kBt. We can justify this by the fact that see, P1 and P2, it's all about probabilities. Okay, as the temperature changes, probabilities are changing. Okay, and it's the probability on which the average energy depends. As I told you people, we calculated the high energy limit by using this formula, and that is actually the formula to calculate the average energy. So it's probability on which it depends basically. And here to see from which point, from which temperature onwards the transition is occurring, the main transition is occurring, like the lower energy limit is changing into higher energy limit, we need to determine that point, and for that purpose we have to look at the probabilities. And since P1 equals minus E1 by kT and P2 equals minus E2 by kT, since the system's energies E1, E2, E3, E4, they are fixed, they are not changing, but probabilities could change depending upon the temperature the system is in. Let's find out the comparisons of these two probabilities. For this, I'm just dividing P1 by P2, and we have E1 by kT here divided by e to the power minus E2 by kT, and we can take this term into the numerator so that it got positive, with it becomes positive power, and we can convert them into a Boltzmann factor form by taking minus common, and we have E1 minus E2 by kT. This is actually delta E by kT. Okay, and there are three parts of this of these terms. Let's write here P1 by P2 equals e to the power minus delta E by kT. There are the three parts this value could have. There is one section, second section, and the third section for the comparison of delta E by kT, as this factor is the determining factor. Okay, that how P1 compares to P2. There is the one region where delta E is less than kT. There is another region where delta E is greater than kT, and there is a region where delta E is comparative to kT. Okay, and since T is changing, none of the other things are changing. Delta E will remain the same for a given system. K is a constant, will remain the same, but temperature is changing. As the temperature is changing, this factor changes. Delta E by kT changes, and this is the higher temperature region, this is the lower temperature region, and which will be the transitioning point. This will be the transitioning point because it's in the central, and at this point when kT becomes large, like it will transition to this state, and when kT is smaller, then it will transition to this. So this is the point where the lower temperature limit values will transition to higher temperature limit values. Okay, that is how we can say it by the comparison of the two probabilities, and the Boltzmann factor helps us to determine the transitioning section. So it is delta E is comparative to kT. At that temperature the transition will occur, and the populations will begin to shift considerably. Okay, besides that point. Okay, that is how we wrote this. All right, delta E, it could be E2 minus E1 or E1 minus E2. It's just difference that matters. It's numerical value, not negative positive thing. Okay, so it's the difference that matters. It will be better to use mod here. Okay, because we are talking about the magnitudes, and yeah, that is how we can see it. Now let me draw the plot, because that's the last thing that is left. In part A we have discussed analytically, we discussed each and every details that were asked in the question. we saw that what will be the lower temperature limit, what would be the higher temperature limit, and what would be the temperature at which the transition would occur. And if you want to find the temperature, you can E2 minus E1, their magnitude divided by Kb will be the temperature at which the transition will occur. So you can write T approximately equals E2 minus E1 bar, so that it is positive, by Kb. This is the temperature at which the transition occurs from lower limiting value to higher limiting value. Let's say this is the lower temperature limit. Here we have temperature, here we have energies, average energy. Let's say this is the lowest possible energy we have, because this is temperature 0 and temperature increases in this side and the energy increases upward. This is the lower possible energy. Let's say it's capital N times E1, and let's say this is the highest most average energy, which is capital N times E1 plus E2 divided by 2. Okay, so this lower temperature limit, it begins to increase and reaches a point where a higher temperature limit is reached, where the average energy becomes equal to this, and the graph becomes flat as the temperature increases, because the higher temperature limit is reached. Okay, this is the qualitative graph here for us, and roughly at, let's say at this temperature, this is the temperature at which the transition is occurring, T E2 minus E1 by Kb. This is the temperature, and we can't determine the average energy at that point because we are not required to do that. We just need to mention these 3 points, and the graph was needed. And this is the higher temperature limit, this is the lower temperature limit, and this is the middle region. All right, so this was the plot 1. Now let's see what is needed in part B of this problem, because it's related to part A, and let me show you. Here's the part B. Using the results of part A, make a qualitative plot of the heat capacity at constant volume as a function of the temperature. Okay, so we have to draw the qualitative plot. Qualitative plots means they should show what the behavior would be. It doesn't need to be accurate. Okay, there could be some errors, but that's not needed. We have to draw the main crux of what the graph would look like. So we need to do it for the heat capacity. This is the part B. Let's do it. For part B, let me first tell you the relationship between the heat capacity and the average energy of the system. And the relation is that heat capacity is given by, we know that the heat capacity is given by, it is actually the energy needed to raise the temperature of the system by 1 Kelvin temperature at constant volume. Okay, this is the heat capacity at constant volume. So actually the slope of E bar T graph will give us the heat capacity. Okay, since we know the graph of E bar, this is the E bar T graph, we can determine the graph for the CV heat capacity from this graph by taking the slope of each and every point here. Okay, this slope will help us to draw the graph for the CV. Let's do that. Slope of this graph is gonna give us the graph for CV. That is why I have drawn it again to justify the shape of the graph that we are gonna get. And this is not something that you should do on a neat paper, okay, or when you are solving it on your exam. All right, this is something that I'm just telling you to, like, you can analyze the graphs this way, and you can draw them on your own, on your, like, just to enhance your capability of reading the graphs. So we have 3 regions. One is the lower temperature region, higher temperature limit, and the central region. So what happens in the really lower temperature region is that average energy is constant here, since you can see that Cv is equals to partial E bar by partial T. So if at low temperature limit average energy is this approximately, there is no temperature in here, and we know that the derivative of a constant quantity is 0. So Cv is approximately, it's always approximation, not exactly, but approximately 0 at lower temperature limit, and it's approximately 0 at higher temperature limit as well, because the average energy becomes constant at the higher temperature region. At a really higher temperature region, average energy nearly becomes constant, and Cv also nearly becomes 0, nearly, not exactly, but a really small value of Cv is there. What happens in the middle region? We have a center point, transitioning point, we know that. So before that, what happens is that the average energy is increasing and the slope is also increasing. The average energy, if we draw the slopes here, we can see the vertical the slope is, the higher the value of slope is, and here slope is actually the heat capacity, as we discussed earlier. So higher slope means higher heat capacity, and from slope, higher slope can be shown on the graph by how vertical the slope is. The more the vertical the slope is, greater its magnitude would be. Okay, and the flattened it is, the minimum its value would be. Okay, this is how we can say about slopes, and by slope it is heat capacity. Keep that in mind. So you can see that here the slope is lesser, but here it is becoming more and more vertical until this point is reached. You can see until this point is reached, here at that point the slope is maximum. Okay, there is a peak is reached, and after that point you would notice that the slope is decreasing, and we can see it by the flattening of the slope line. Slope line is obtained by drawing a tangent by drawing a tangent at each point on the graph, you get the slope. Okay, and you can see that the slope is getting flattened and flattened until it becomes really horizontal at the higher temperature limit. Okay, the slope is increasing from this point until a maximum point. This point is reached nearly this temperature, nearly, not exactly. We don't, I can't say anything about it, we need to do it to do the exact calculation, but nearly at this temperature. And after that we can see the slope is getting flattened. It means the heat capacity is decreasing until it becomes nearly 0. Okay, this is the kind of shape we are gonna get. Now let me draw this graph, and Cv graph, part B, Cv graph, Cvt graph. This is Cv, this is T. As we saw, at lower temperature limit the Cv would be 0, not exactly, but really nearly equal to 0. So I'm starting not exactly touching the 0 line, but essentially from 0. So it increases until it reaches a maximum value, this maximum value. Then it decreases, as I told you people, it increases until this point is reached. After that it decreases until it becomes nearly 0 and becomes flattened onwards. And flattened onwards means this, like this. As temperature increases, it's nearly 0, not exactly, but nearly 0. Alright, this is the Cv graph. So that was needed in part B. Now let's do the part C. Here's the part C. Calculate explicitly the mean energy E bar of T and the heat capacity of this system. Verify that your expressions exhibit the qualitative features discussed in part A and part B. Okay, we have to calculate here the expression for the mean energy and heat capacity of the system, okay, in general. And then we have to verify that what we answered in part A and B or are having an agreement with our mathematical formula. Okay, so we have to derive from these actual formulas of heat capacities and mean energy. that what they would be at low temperature and high temperature and the transitioning thing. Okay, we have to justify them by these mathematical thing. In part A and B, we just analytically suggested and guessed that what it would look like, but in part C we have to tell them that yes, we were right. So let's derive an expression for mean energy and heat capacity for the system. That is really easy. It's time to calculate the actual expression for the mean energy, and this is the formula as I told you people earlier. The mean energy of the whole system containing capital N number of particles is equals to this. Let's insert all of these values right into this expression. We know the value of P1 and P2, and we can directly insert those values right here. And P1 is the probability of the particles to be in E1 state divided by Z, which is the partition function, and the partition function of this system is simply the Boltzmann factor for E1 and for E2 state, the sum of it. This is actually the partition function plus E2 e to the power minus E2 by kt for P2, and the same partition function, which is this. I hope you know how to calculate partition function. It's actually this summation which runs for all the possible states. Since and here since we have only two states, then we wrote it for E1 and E2 and sum of it, which is this simply. All right, now we can actually since the denominators are same, we can write the above term in a single denominator, E1 e to the power minus E1 by kt, or simply we took the LCM. All right, now we need to convert them into a form that is more easy. For that purpose, I am dividing e to the power minus E1 by kt by each of the expressions above and below, divided by e to the power minus E1 by kt plus E2 e to the power minus E2 by kt divided by e to the power minus E1 by kt divided by e to the power minus E1 by kt divided by E1 by kt plus e to the power minus E2 by kt divided by e to the power minus E1 by kt, just to get a form where we'll get delta E. Okay, this cancels out, so we are left with E1 plus E2 e to the power minus E2 by kt. Then it is negative power in the denominator, it will become positive power in the numerator, and since both are under the base E, I am writing them under a common base E. 1 plus this becomes 1, and e to the power minus E2 by kt, and it gets into the numerator with the positive power. E1 plus E2 e to the power, we can write it like that, E1 minus E2 by kt. Okay, just I wrote E1 first and E2 second and took the LCM since they were both kt, so I wrote them under the same term, and this is the average energy so far. Let's call it as equation number A. Before I do something else, I need to do one more step here. You can see here it's E1 minus E2, and E1 is less than E2, we know that. Okay, that's given. Since E1 is less than E2, so E1 minus E2 will result a negative quantity always, because E1 is lesser than E2. Like E1 is, let's say, 2, then E2 is 3, so it's negative 1. The result we'll get is negative. So I want to write it like greater quantity minus smaller quantity. Okay, so I'm taking negative as common, so we are having E2 minus E1 divided by kt. That's needed because when I'll put the limits, that fact would be needed. It's negative E2 minus E1 by kt. Okay, that is why I'm doing it. So this is equation number B, and this is the expression for the average energy. Now, as t approaches to 0, let's put t approaches to 0, then what happens is e2 minus e1 by kt, it's t in the denominator, it becomes infinity because it's 0 in the denominator and 1 over 0 is infinity. So we can put infinity into this expression, e1 plus e2, e to the power negative is always there, okay. In place of this whole quantity we'll write infinity, and in denominator 1 plus e to the power minus infinity as well, and e to the power minus infinity is 0, okay, because e to the power minus infinity is equals to 1 over e to the power plus infinity, and e to the power plus infinity is infinity, and 1 over infinity is 0. That is why I stressed upon this fact that this result is always negative, and negative power is a fact that is needed here to put this limit. So this becomes 0, this becomes 0, and we are left with an e1 plus 0, because this becomes 0 and 0 multiplies with e to become 0 again, and it's 1 plus 0, so it's it will become E1 times capital N, which is the average energy at the lower temperature limit. This is the average energy at lower temperature limit. Now let's do it for the higher temperature limit. We can write here limit T approaches to 0 as well. Here now applying the higher temperature limit, higher temperature limit on B, limit T approaches to infinity, E bar equals capital N E1 plus E2 e to the power minus E2 minus E1 divided by k into infinity. It's like e to the power minus 1 over infinity, and we know that 1 over infinity is 0, so e to the power minus 0, e to the plus minus 0 is 0, so e to the power 0, which is equals to 1. Alright, so this is what's gonna happen now. E to the power 0, I'm gonna write it simply, or simply 1 over infinity, because everything else multiplies with infinity to become infinity. It's e1 plus e2 e to the power 0, 1 plus e to the power 0, capital N e1 plus e2 e to the power 0 is 1 again, which multiplies with e to become e2 simply, and it's 1 in place of this, so capital N e1 plus e2 divided by 2. This is the average energy at the limit of higher temperature. Now we need to calculate the specific heat. Cv is equals to partial E bar by partial T at constant volume. Let's continue. Here we know that what is the average energy. It's capital N E1 plus E2 e to the power minus E2 minus E1 divided by KT, 1 plus e to the power minus E2 minus E1 divided by KT. So this is the average energy. Capital N is constant, so we can take it outside, and let me write this expression like that so that we can apply a simple product rule on it. Sometimes we just forget the quotient rule of derivatives, and product rule is really easy and there is no confusion in it. That is why I prefer using product rule, and this is the whole thing, and we can write it in brackets, and it has a whole power plus 1, and if we take it into the numerator, the whole power becomes minus 1. And now we can use the product rule, where we have this as the first term and this is the second term, and I have to start from here because there will be some lengthy terms, but they will be simplified really quick. Let's start. This is the first term as it is, bracket close, derivative of second term, then plus sign, second term as it is, derivative of first term. Bracket close, this bigger bracket, and capital N into, let's start the process. I'm writing here the first term, which will remain unchanged, and we have the second term. We'll use the power rule on it, in which the power will come in the start. Okay, the power, whatever the power is, we'll write it here. Then the whole thing that we have here, and the power is subtracted by one number. Okay, I hope you know the power rule of differentiation. It works like that. For example, if we have this thing, then power comes in the start, and we have x, and power is reduced by one digit, dot the inner term's derivative, the term which is under the power, its derivative is also taken, whatever that term is. Okay, so that is how the power rule of differentiation works. So power is here, then power is reduced by one number, then we have derivative of inner term. Since we are taking the derivative with respect to temperature, so it's delta by delta t of this inner term, which is 1 plus e to the power minus e2 minus e1 by kt. This is the inner term whose derivative will be taken in next step. And we have plus sign. We write this term as it is. We are not taking anything in the denominator because the terms are really lengthy, and until unless we could reduce them into some smaller form, we'll not write anything in the denominator to avoid confusion. So these all terms are in the numerator. This is one line, and derivative of this inner term, it's two terms in here. Derivative of e1 will be 0 because there is no t in here, its derivative will be 0, and derivative will be applied on here, and e2 remains the same because it's a constant. Then derivative of exponential function, which is exponential function as it is, dot derivative of its power, e2 minus e1 by kt, and this negative sign I'm writing here. Okay, this negative because there is no place to write here. Power is negative into e2 minus e1 divided by kt, so the whole thing needs to be written, and the whole bracket close. Capital N, e1 plus e2 e to the power minus e2 minus e1 divided by kt. These lengthy calculations are always annoying for me. They are so lengthy. Negative 1, and this power becomes negative 2. Okay, so 1 plus e to the power minus e2 minus e1 by kt whole negative 2. And derivative of inner term, now derivative of 1 will be 0, and derivative of this term will be non-zero, and the derivative of this term is exponential term as it is, derivative of its power, which will bring e2 minus e1 divided by kt, in this negative sign I'm writing here. Okay, so again in the continuation of this term, e2 minus e1 by k are constants, so I'm taking them outside. Partial by partial t of 1 over t, it's like partial by partial of 1 over t is left, which is equals to minus 1 over t square. Okay, you can see the derivative rule, this that is equals to 1 over x square minus 1 over x square. Okay, so we can simply write here minus 1 over t square, bracket close. capital N E1 plus E2 e to the power minus E2 minus E1 by kt. This negative sign and this negative sign becomes positive, and this whole term is negative 2 in power in the numerator. It becomes positive power in the denominator. This whole power becomes positive 2 in the denominator, and we have this term e to the power minus E2 minus E1 by kt, and again E2 minus E1 by k, and the derivative of 1 over t is minus 1 over t square. Okay, and this negative sign and this negative sign cancels out and it becomes positive. Here this term is negative power in the numerator and becomes positive power in the denominator. I am just now decreasing the number of terms in the numerator, and this is negative negative positive E2 into E2 minus E1 by kt square E2 minus E1. This is E2 and one term is left, it's E2 minus E1 by kt. Now we can see here E2 minus E1 by kt square, this term, and here it's also there E2 minus E1 by kt square. We can take it common. This term could be taken as common, as well as this term could be taken as common. So let's take them common from both the terms and write them alongside capital N so that some rush is reduced. K by kt, and we have E2 minus E1, we took it common, divided by kt square. So we are left with this negative sign is here, okay, so it's written there, and we have this whole term, and I am multiplying negative sign inside as well. Kt, and in division we have 1 plus E2 minus E1 by kt whole square, plus only E2 is here, all other terms are taken as common. One or two more steps and it's sorted. Okay, only one or more steps are left, so we can take LCM. We can see both of them inner terms are same, it's just a square here and it's whole power 1 here in the denominator. So we can take LCM, or one more thing, like let's take this term common as well from the whole quantity so that we can write it here. Okay, 1 plus e to the power minus E2 minus E1 by kt whole square. Okay, I'm taking this term common, which means that I'm multiplying this term with both of these quantities so that this one cancels out. I took it common, plus E2 into only one of them is left. For example, I took this term common from the whole quantity. Taking a term common means if it is in the denominator, okay, I took it common from the denominator, so it means multiplying this term in the numerator of each term inside so that it's written in the denominator outside. Okay, it's written in the denominator outside, so what I did here is I multiplied this same quantity, let's say it's a square inside, since there where a is this inner term. Okay, so a square cancel out and there is nothing in there, and only one a is cancelled here, so only a is left in the numerator because it's not the square in the denominator. Okay, I hope you got it. I really hope you got it what I did here. Otherwise you can simply take the LCM. It's the other way you can do that. Okay, so capital N I'm writing e2 minus e1 here, e to the power minus e2 minus e1 by kt divided by 1 plus e to the power minus e2 minus e1 by kt whole squared kt square. Okay, now let's simplify. Inside only one or two steps are left. E to the power minus e2 minus e1 by kt as it is, and I'm multiplying e2 inside, so it's e2 plus e2 multiplies with 1 to become e2 multiplies with this quantity e2 e to the power minus e2 minus e1 divided by kt brackets close. This and this cancels out. Okay, it's negative e2 e to the power this, it's plus e2 e to the power this, so it's e2 minus e1 that is left behind, and this is e2 minus e1, or we can write it as e2 minus e1. This is left here, e2 minus e1, and this is e2 minus e1 as well, so it becomes square. I'm just reducing the number of steps. Okay, you have to write it in next steps. So it becomes square here, and this is the final term as well for CV. This is a heat capacity term. Let me write it again. It's CV equals capital N E2 minus E1 whole square by KT square. I'm writing it first here. Then we have e to the power minus E2 minus E1 by KT, and in the denominator we have one more term, 1 plus e to the power minus E2 minus E1 by KT whole square. This is the heat capacity formula for the given configuration we have in the question, and let's see what happens as t approaches to 0 or t approaches to infinity. And we can also check it from the formula itself. If we put CV equals 0, so we have capital N E2 minus E1 whole square e to the power minus E2. We can determine the temperature from it where the CV would be 0. This is alternative method to do that. Whole square equals 0. Okay, and we can see that these are constants. They will go into the other side of the equation to be vanished, and we are left with 1 over t square. This as well, only t terms I'm writing here. Whole square equals 0. This term in the denominator is not a determining term because it can never become 0, and it can never become infinity as well. Now, what are the ways to make a thing equal to 0? Okay, those terms which are in the denominator, they can make a whole quantity 0 if the denominators are equals to infinity. Which means, for example, if t in the denominator is equals to infinity, we'll have 1 over infinity, which would be equals to 0. There is one way the denominators can make a thing equal to 0, that is when the denominators are infinity. So when t approaches to infinity, we can say when t approaches to infinity, then CV would be equals to 0. From this statement, 1 over t square equals 0, we can say that. So we can write here like either 1 over t square should be equals to 0, or this quantity should be equals to 0. This can only be equals to 0 if t approaches to infinity. Okay, then CV equals to 0. This is the one condition we get from this statement. Now what about this one? Here this quantity can become 0, the numerator can become 0 when t is 0 here, because what happens here that if t is 0, then it will be like this situation, and 1 over 0 is infinity, e to the power minus infinity, which is equals to 0. Hence, as t approaches to 0, CV becomes 0. They are the two conditions. The denominator here is not a determining term because it can never become 0 and it can never become infinity as well. Okay, there is no way the denominator here, because this quantity can never be infinity, it can never be 0 as well. You can test it. You can put t is equals to 0 here, you can put t is equals to infinity here. This whole quantity 1 plus this quantity can never become 0 or infinity. Okay, that is why this is not determining term, but this is the determining term. This term becomes 0 when t is 0. Okay, and this term becomes 0 when t is infinity. So we can see here that cv will be 0 either when t approaches to 0 or t approaches to infinity. They are the two cases. Hence we can see our predictions in part A and B were correct. And that is the end of this problem. One thing that we missed is we didn't justify the temperature at which the transition is occurring from lower limiting value to the higher limiting value. Okay, we need to find out the temperature and prove it that it is equals to E2 minus E1 by kb. Okay, that is something that we need to prove, and we hadn't yet. So for that purpose, we know the value, average energy value at low temperature limit is this, while the average energy value at the higher temperature limit is this. Transition would occur when there is half here and half here, half molecules here, half of the particles or molecules whatever are here. Okay, such that the total number of particles are this. Okay, which is the point. What is the point when half of the particles are at lower energy limit and half of the particles are now at the higher energy limit? Okay, the point at which this happens is the transitioning point, because above that temperature what would happen, that particles would move in these particles, more of these particles would move in this state, so this thing will become dominant and they will achieve the high temperature limit. And if we lower the temperature than this value, then what will happen, that these particles will move in this energy state and this value begins to increase and until it becomes capital Ne1. Okay, so this is the total energy at the point where the transition will occur. So we have the transition would occur, the total energy, the average energy equals E1 by 2 plus N by 2 E1 plus E2 by 2. Okay, this is the average energy at high temperature limit, and this is the average energy at low temperature limit. So half of them will be taken, and this is the average energy. And what expression we calculated was capital N. We'll set it equals to the general expression that we got, that was E1 plus e to the power minus E2 minus E1 by kt. We need to calculate t. So we'll do that. 1 plus this n and this n will be cancelled out. So we are left with E1 by 2 plus E1 plus E2 by 4. 2 2s are 4 here, and that should be equals to E1 plus e to the power minus E2 minus E1 by kt divided by 1 plus e to the power minus E2 minus E1 by kt. Let's take LCM here, so the LCM is 4. It's 2E1 here plus E1 plus E2, that is equals to E1 plus E2, this exponential thing, and plus negative and this thing. Okay, so it will become 2E1 plus E1 is 3E1 plus E2 by 4, 3E1 plus E2 by 4, and that is equals to E1 plus E2 e to the power negative this exponential 1 plus e to the power negative this exponential. Will cross multiply, this will be multiplied this side, and 4 could be multiplied this side. So it's 3E1 plus E2 into 1 plus e to the power negative E2 minus E1 by kt, that is equals to 4E1 plus 4E2 e to the power negative E2 minus E1 by kt. Let's simplify, we'll multiply it inside. So 3E1 plus 3 into this exponential term, plus now this will be multiplied E2 plus E2 this exponential thing, 4E1 plus 4E2 e to the power negative this exponential thing. Now this is 4e2 and there is e2 with exponential thing here as well. We can take it to this side of the equation and we can take 4e1 here. So it becomes 3e1 minus 4e1, this one. Then this term 3e1 e to the power negative exponential plus e2 equals 4e2 e to the power negative exponential, and this will be subtracted here. 3e1 minus 4e1 is minus e1. This is plus e2 plus 3e1, this negative exponential. Then we have 4, it becomes 3e2 e to the power negative exponential. Let's simplify it further on. Minus e1 plus e2 plus 3e1 e to the power negative exponential, let's write it now, equals 3e2 e to the power negative e2 minus e1 by kt. Now what else we can do is we can write them together. No. What we can do is e2 minus e1 is one term plus we can take this to the other side of the equation. So it's plus 0. 3 e to the power e2 minus e1. This will be subtracted here. 3e1 e to the power negative exponential. e2 minus e1 equals 3, and this exponential could be taken common by kt, and we are left with e2 minus e1. They are cancelled, so it's 1 here left. 1 3 2 minus e1 by kt, 1 over 3. It's 1 over 3 could be divided here. We need temperature, so we need to bring it outside of this exponential thing. It's an exponent. For that purpose, what we are gonna do is take natural log on both sides, and it's the property of natural log that we can write it like that: natural log of numerator minus natural log of denominator. Okay, natural log of 1 minus natural log of 3, that is equals to, and here it's the property of natural log that the exponent will come in as the coefficient, and natural log of e is left. Natural log of 1 is 0 minus natural log of 3 equals negative e2 minus e1 by kt. Natural log of e is 1, so here it's negative sign and this negative sign cancels out. Natural log of 3 equals e2 minus e1 by kt. So if we take temperature here, it's kb into natural log of 3. Okay, and if you find out the value of natural log of 3, that is approximately equals to 1, we can make that approximation. So now t is equals e2 minus e1, we can use this approximation sign by kb. Okay, that is proved, because what we needed is to say that roughly at which temperature that transition would occur. So roughly we can take natural log of 3 approximately equals to 1, and roughly this is the temperature, and that is proved as well. Okay, this was the last part, and yeah, we calculated average energy as well as heat capacity, and we saw their extreme values, and we proved that what we have predicted was correct. Okay, so that is it for this video. I'll meet you in next video. Till then, take care, like, share and subscribe. Goodbye. Additionally, if you have any queries, you can ask me in comment section.